All right, let's dive into a story that's been 65 years in the making. It's all about the simple, universal quest to find the fastest way to get from point A to point B. But this isn't just about maps. It's a tale of a long-reigning king, a supposedly unbreakable barrier, and a brand new challenger that might just rewrite the rules for everything.
You've probably never heard its name, but there's a single, brilliant algorithm from way back in 1956 that has been the quiet engine behind our modern world. Seriously, every time you pull up directions, every time you send a message, it's there, working in the background, making lightning-fast decisions for you.
So, before we can get to the new kid on the block, we absolutely have to pay our respects to the reigning king of all things routing. And its name is Dijkstra's algorithm.
I mean, this one idea, this shortest path problem, is constantly running our lives from behind the scenes. It's what gets your GPS to navigate around a traffic jam. It's how this explainer travels across the internet to reach you. And it's even how a delivery service figures out the most efficient route to drop off a package at your door.
For over 60 years, this algorithm has been the gold standard, the first thing you learn in any computer science class. It's elegant, it's smart, and it's super reliable. Imagine you're exploring a city on foot. Dijkstra is like starting where you are, finding the absolute closest intersection you haven't visited, walking there, and then from all the points you now know, finding the next closest one. It's careful, it's methodical, and it's pretty much guaranteed to work. Well, almost.
Yeah, that almost is a big deal. Because as great as Dijkstra's algorithm is, its reign isn't absolute. It has one critical weakness. It's kryptonite, a scenario where all of its beautiful, simple logic just completely falls apart.
So what on earth is a negative weight? It's not like you're traveling negative miles, right? No, think of it more like a rebate or a profit. Imagine a route where one of the roads is a special toll road that actually pays you money to drive on it. See the problem? Dijkstras always find the closest logic breaks because you could just keep looping on that road that pays you and the path would get cheaper the longer you drive.
So, when you've got those tricky negative costs, computer scientists have to pull another tool out of the box, the Bellman-Ford algorithm. But, and this is a huge but, there's a massive trade-off. Bellman-Ford can handle the weird stuff, but it is way, way slower. And when you're dealing with the gigantic networks that run our world, that difference in speed is a total deal breaker.
So how does Bellman-Ford work? Well, it thinks about the problem in a completely different way. It doesn't do that careful one-step-at-a-time thing. Instead, it starts out, well, really pessimistic. It basically says, okay, I'm at my starting point, so that costs 0, but I have no idea how to get anywhere else, so I'm just going to assume every other place is infinitely far away.
Then it starts this process called relaxation, which is a fancy term for what's basically spreading a rumor. It goes through every single road in the entire network and asks a simple question. Hey, is the path through here shorter than what I currently think is the best way? If the answer is yes, it updates its best guess and slowly, gradually starts to build a more accurate map.
And it doesn't just do this once, it does it over and over and over again, checking every single path repeatedly. It's kind of a brute force approach, which is exactly why it's so much slower, but that's also why it can handle those tricky negative costs. And you'll want to remember this totally different strategy, because it's a huge piece of the puzzle for the breakthrough we're about to see.
Okay, so let's recap. Dijkstra is fast but can't handle negative costs. Bellman-Ford can, but it's slow. So for all the normal, everyday stuff, just getting from A to B, Dijkstra's is still the champ, right? For decades, everyone thought so. But it turns out it had a completely different Achilles heel, a fundamental speed limit.
So here's the thing. Remember how Dijkstra's whole strategy is to find the absolute next closest point? Well, to do that, every single time it takes a step, it has to look at all of its immediate options and sort them from nearest to farthest. And all that constant sorting, well, as this quote puts it, you end up spending a whole lot of your time just getting organized.
This became known as the sorting barrier and was this legendary wall in computer science. For something like 40 years, the common wisdom was just, nope, you can't get any faster. The very logic of the algorithm is sorting, so you're always going to be limited by how fast you can sort. End of story.
End of story. Until 2024, when a team of researchers from Tsinghua University, Stanford, and the Max Planck Institute came along and basically said, you know what, we think we can break that barrier.
This new algorithm is just so clever. It doesn't try to be a faster version of Dijkstra. Instead, it completely changes the rules of the game by mashing the two classic approaches together. And it all started with this one kind of radical idea. What if you didn't have to be so methodical? What if you could just skip a few steps?
Okay, check this out. The new strategy starts exploring just like Dijkstra. But, and here's the genius part, instead of getting bogged down meticulously sorting every single side street to find the absolute closest one, it pauses. It runs just a few quick rounds of that slower Bellman-Ford method, not to find the final answer, but just to scout ahead and get a hint of where the really important intersections are. You know, the major highways. And once it finds those, bam! It just jumps straight to those promising points, completely leapfrogging the tedious work of sorting all the little streets in between.
So, the big question, right? Is this it? After 65 years, is the king finally dethroned? Well, the answer is a really fascinating yes, but. See, this new algorithm's victory happens on a very specific battlefield, something called sparse graphs. Just look at the image on the left. That's a roadmap. Any given city is only directly connected to a handful of other cities. The network is sparse. Now, the image on the right, that's a dense graph. Think of a tight-knit group of friends where everybody knows everybody else. Connections everywhere. And here is the kicker. This is why this breakthrough is such a massive deal. Because as this person points out, almost all of the networks that actually matter in the real world, the internet, our power grids, shipping routes, they're all sparse. They look way more like that roadmap than that super-connected social group. Now, don't get scared by the math here. You don't need to be a computer scientist to get this. See that log n part in Dijkstra's formula? That's it. That's the sorting barrier. That's the speed limit we've been talking about. Now look at the new algorithm's formula. They've replaced that term with something that grows way more slowly. In simple terms, they didn't just bend the rules, they smashed that old speed limit. It is officially, mathematically faster on the kinds of networks we use every single day.
So let's just take a second to appreciate what this means. This isn't just some small, nerdy tweak. It's a fundamental shift in how we think about one of the most classic problems in computing.
And you know what's maybe the most impressive part of all this? They didn't invent some kind of crazy new math to do it. The tools they used have been sitting there for decades. It's like someone finally realized that by combining a hammer and a screwdriver in a clever way, you could make a brand new tool that nobody had ever imagined. It's just a story of pure, brilliant ingenuity. So yeah, this breakthrough might mean we get slightly faster GPS directions, but the real story is so much bigger. It proves that even the most fundamental ideas, things we thought were solved for over half a century, can be completely reimagined. It opens a brand new chapter in a very old story. And it just makes you wonder, what other unbreakable limits are we living with right now, just waiting for the right clever idea to come along and shatter them?